Okay, so hello everyone. Thank you very much for being here. My name is Tarek Elgohary. I'm an assistant professor at the MAE department. A little bit about myself. I had master and Ph.D. from Texas A&M University. I worked there for about a year for a postdoc, and I joined UCF in 2016. My main areas of research are in astrodynamics, space situational awareness, computational methods, and applied to a discrete element method, optimal control, and finally a little bit of robotics for space missions. Some of the courses also I taught here are also all related to dynamics control, astrodynamics, and guidance navigation and control. So I'm gonna go very quickly about the various topics that we are exploring in my lab. And we start with my main area, which is astrodynamics and space situational awareness. And you see here, this is the current outlook of the space environment with all the debris being tracked by various agencies like NASA, the Air Force, and so on, and also the European agencies. And you see here, this is a draft or a graph for the increasing number of space debris that is being tracked. And this is just what we can track. The reality is there is probably an order of magnitude more objects in space in form of debris. And there is a phenomenon called Kessler syndrome that they keep colliding and essentially exponentially increase the number of debris in the space environment. So in order to sustain or to have a sustainable space environment, we focus on astrodynamics research and uncertainty quantification and applying those to space situational awareness. So this plot here shows you that after only one orbit, this is the probability density distribution of this green dot here of a certain when we start Gaussian, just because of the nonlinearity of the problem. And obviously this is the way the two-body problem look like. So a couple of things that we have been working on. One area is obviously related to observations. So most of the current observation systems are ground-based. The tracks are sparse, and the conjunction analysis can be quite challenging. Essentially, how to match an observed object to a later observation, and so on and so forth, to keep the catalog alive. And essentially, a lot of research has been done in what if we included space-based observations. Now, space-based observations obviously are generally expensive to apply on a large scale. And if you are going to cheaper type options, you have to use what is known as angles only, and basically relying on a camera. And for angles only, there have been several challenges in terms of observability. And what we recently came up with and most recently published was a way to introduce a multinodal system, essentially to form a network of observations to improve the observability of the space-based problem. And essentially, this is just a cartoon of what we anticipate it would look like. And that's the structure we got. And you can see each node is sort of separate in the structure of the problem. And you can add and remove nodes based on their observability. And one experiment, numerical experiment we have here is that when you have bad measurements, you see the filter is diverging. And just by removing that node from that structure, the filter converges to very high accuracy. So this problem is interesting because it provides the scalability needed for something like that, for a space-based observation network. One of the ideas we thought of is space traffic management in the sense of highway cameras, if you will, and essentially providing those, if you want to observe a specific patch of the sky, you can place those CubeSat type or cheaper, nothing in cheap in space, but cheaper satellites, and essentially provide sort of a highway camera for continuous traffic. It could be also applied for the cislunar environment, and even as a defense mechanism for, or an identification mechanism for near-Earth objects, which we only catalog about 15 to 20% of them that are known to us. with the current technology. So this is one project that we're working on. The other area that is also related to uncertainty and estimation, and I'm sorry about all the equations, I'm gonna go through them very quickly. But the point that I wanna make here is that there is a way, a close cousin to this problem is the estimation problem. And estimation problems require sensitivity matrices in general, if you're in the Kalman filter type regime. And if in that case, you need to model, you need to have an accurate model of the process. And what is currently available is what is known as like the simplified model. So what we're developing here is a way to efficiently compute the perturbed state transition tensors, or the sensitivity matrices, to include them in our linear prediction type results. So it is based on a very simple idea of Taylor series expansion right there, and just coming up with some variables that can be recursively computed to provide the necessary partials to compute the higher order state transition, the first order state transition matrix and the higher order state transition tensors, if you will. And here, this is just a demonstration. If we have just the first order state transition matrix, we get an error of kilometers. With the second order state transition matrix, we get 2 orders of magnitude reduction in our prediction results. And this is along the path of 10 orbits. We have tested this on thousands and 10,000s of orbits, and this paper is now under, we submitted the revision just a few weeks ago. So, so we're working on this area basically to provide a better estimation for the previous problem, and also to provide a better way to compute the state transition tensor for general astrodynamics. The third part of this problem is obviously uncertainty quantification. So if you're outside of the EKF framework, the extended Kalman filter framework, and you want to go into the unscented Kalman filter framework or any consensus type filters, you have to essentially consider how to quantify uncertainty and how to propagate uncertainty. And this is where some of the computational techniques and approximation techniques that we have developed, or we are still in development, essentially how to use some distribution of nodes here and essentially compute the overlap, and how we can approximate the probability density function of 2 resident space objects, compute the probability of collision, and come up with the total probability of collision and the distribution accordingly in an accurate manner. Obviously, this has been done right now. If you want a high fidelity solution, you have to do Monte Carlo for hundreds and hundreds of hours, or use some surrogate modeling, which is less accurate and suffers from the curse of dimensionality. What we're looking at is a way to overcome the curse of dimensionality by using some adaptive approximation techniques that basically places the nodes where they are needed versus the general approximation method. And we have some preliminary results there. Just to show a cool video of how the uncertainty or the probability density morphs. This is just one cycle of a nonlinear system. And what starts as Gaussian ends up as this banana-shaped type distribution. So it's very, very hard to approximate these things with the assumption of Gaussian or of Gaussian distribution. And this is just one orbit or one cycle of a non-linear system. So if you want to propagate uncertainty for orbits and thousands of orbits, the approximation here becomes very, very challenging. A little bit unrelated to the previous problem, which is a problem that we have been recently looking at, is the dynamics of lunar dust particles. And essentially, it is motivated by the fact that in the Apollo missions, you can see here the dust clouds in the lander and dust clouds in the rover are forming. And the observation proved that those dust clouds, they don't follow ballistic trajectory. They keep hanging up in the air. We are anticipating more and more missions to the moon. So we need to understand how the dust propagates from lifting off and landing, and how it can accumulate on various assets surrounding the landing site, and obviously habitats and all the cool stuff we have been hearing about. So we're looking at this problem from a dynamical system, a multi-body dynamical system, and we're trying to do modeling of the electrostatic forces, the gravitational forces, the tribocharging or its charge exchange. And we've been using for that discrete element methods, we've been running some experiments to show how particles interact and how various, how the charge can exchange from particles to another, how it's affected by gravity. This video here shows how it is affected by some vibrations of the plate, and also accounting for charge exchange. And this project has several contributions to the general physics. I'm collaborating with the physics department, Dr. Dove, essentially into understanding tribocharging and essentially better modeling of the lunar environment for mitigation and for various future missions. All right, so another area that we're looking at is obviously optimal control, and this is based on an Army project that they were interested in how can they identify what is the best path, or how they can identify something like maneuverability. What we proposed is to follow optimal control theory. And essentially, we're looking at new computational techniques to perform the optimal control problem in real time so that you can have a decision about the feasibility of the solution. And then the target of the ARL project was to basically use something like the cost function to identify the maneuverability of a designed aircraft that can be deployed in the field. So here are some examples of some new computation methods that we have basically been exploring. We know that we do suffer from what is known as the Runge's phenomenon or Gibbs phenomenon when we do approximation. We came up with this, or didn't came up with this. We are exploring this new functions to essentially avoid the Runge's phenomenon and applied it to some minimum time, minimum energy, and various other optimal control ideas. And finally, a little bit of robotics that we're doing in the lab. Essentially, we're building this very fancy robotic platform. It's not very fancy, but it is a very cool project that I have with a bunch of our students. They are very talented. One of them actually went to the AFRL at New Mexico that does exactly that just because of their paper on that. So we're basically marrying a platform, a moving platform with a robotic arm, basically creating a moving manipulator. And for here, we're using a resolved rate type control to essentially emulate orbit motion. This is a work in progress still. We're building another one of those to avoid all the mistakes we made on this one. Obviously, you can see a lot of mistakes already there, but if you don't, that's good. But we're building another one that essentially uses what we have learned from this. And
we need to wrap up soon.
Yeah, this is the last slide. And essentially what we're doing is going to do some orbit servicing mission. This is some future collaborations in UQ, uncertainty quantification for SSA application. We want to couple CFD techniques with the D discrete element method. So if anyone is doing CFD in that regime for the lunar dust problem and plasma physics, and then expansion of the optimal control techniques to model predictive control and dynamic programming, and finally transfer learning and optimization and control if somebody is interested in that. We've been looking into that. Finally, I'd like to acknowledge all my grad students, undergrad students, collaborators, and the current funding agencies.